function that an isoperimetric function can take. And we're also going to discuss subgroups if there's time at the end. So I'm going to start by reminding you a bit of what we did yesterday. So we discussed that then functions quantify the word problem in the sense that the complexity of the word problem is reflected in the growth type of the then function of the group. We also discussed that the growth type of the then function and the solvability of the word problem are quasi-isometry invariants for finitely represented groups. And we commented on the fact that this is no longer true if we reduce the hypothesis to not finitely represented. So to the general class of finitely generated groups. We also saw that the word problem is solvable in G if and only if the then function of G is recursive. And we saw that this was equivalent to asking for any isoperimetric function for the group to be recursive. We also saw that the then function of a group is linear if and only if the group is hyperbolic. So this is a characterization of hyperbolicity. This is equivalent to the definition to being hyperbolic. And we saw a bunch of examples of groups with a quadratic then function, a whole class of them, of a wide variety. And we saw that it's sort of unclear what they have in common. There are many examples. It's not clear what they have in common other than the fact that they have a quadratic then function. So that's still sort of a bit mysterious. And we finished by commenting on nilpotent groups, which are a big class of examples of groups that have polynomial then functions. So we saw that in general, nilpotent groups have then functions that are bounded above by a polynomial, whose degree is at most one more than the class of the nilpotent group. And we saw that when the nilpotent group is free, the bound is sharp. And we also commented on the fact that there are examples of nilpotent groups whose then function is of the type n to the d, where d is not a natural number. So they aren't exactly polynomials. But still they are bounded above by polynomials. So far, all the examples we have seen are groups whose then function is of a growth type that is bounded above by a polynomial. And now I want to remedy that. I want to start discussing some examples where that is not the case, where the growth is much quicker. Okay. So the example we're going to focus on first is Bohm-Exciter groups. So we mentioned Bohm-Exciter groups yesterday when I was mentioning examples of groups that are not hyperbolic. Let me remind you of the presentation. They have two generators and they have a variation. So they are one-reactor groups and they are H and N extensions of Z. Some examples are BS11, which is just Z squared, BS1 minus 1, which is just the fundamental group of the Klein bottle, so the Klein bottle group. So this one is the fundamental group of the Taurus, and this is the fundamental group of the Klein bottle. And we also know that the Bohm-Exciter groups BS and N are isomorphic to the Bohm-Exciter groups BS minus M minus N. This is an easy exercise. But the main example we're going to be interested in is BS12. So BS12 is given by this presentation. Its presentation complex is given by taking a bouquet of two circles and gluing in a pentagon. 1, 2, 3. But I'm actually not going to want to draw the pentagon this way. I'm going to draw it this way instead. So I'm going to draw it as a sort of rectangle with one side subdivided. The labels on the sides are so A, B, A, B inverse, A inverse, A inverse, B. And the universal cover of the presentation complex is the KE complex, which is this one. So Sammy made this drawing.
This is part of the Cayley complex of BS23. Just
oh, okay.
Strictly speaking, yeah.
It looks like BS12. I thought it was BS12. Oh wait, whatever. It's very similar. Okay, so BS12 has an exponential dense function, and that is what we're going to be discussing for the next few minutes. Okay, so we're going to be looking at diagrams of this form. So this diagram right here is a diagram in the KE complex of BS12. So you can see that it's made up of gluing together cells of this kind. And the kind of diagrams that we're going to be interested in are the ones that correspond to these sort of words. So they have the boundary reads the word b to the n, b to the minus n. This is this whole line here. Then a, b to the n. And then this whole line right here. So this should be actually subdivided on this side. This reads a to the minus 2 to the n. Okay, so we can see that this diagram, in the first column, it has 1, 2 cell. In the second column, it has 2 cells, and so on. And in the nth column, it has 2 to the n, 2 cells. So it has an exponential amount of area. But if you look at the boundary, if you look at the word that defines this diagram, we have these cells right here, the ones that correspond to a to the minus 2 to the n. And this is also an exponential amount. So the area of the diagram is exponential, but also the length of the boundary is exponential. So that's not what we want, because we want the area to be exponential in the length of the boundary, and not them to grow at the same rate. But we have a way of remedying this. So let me get rid of the clutter here. And what we're going to do is the following thing. We're going to take this diagram, and we're going to take its mirror image. So I'm going to take this diagram. I'm supposed to be mirroring it, but I cannot mirror it in this application, so I'm just rotating it. And we're going to glue it to the original diagram, but we cannot glue it perfectly. So it doesn't match like this, because if you look at the labels on the sides, this would cancel out. So the way that we avoid this is by gluing with an offset of 1. So I'm gluing these two diagrams together like this. And the diagram I get as a result has this word as its boundary. So depending on, this should be n's. So depending on the depth of the diagram is which n we are at. This diagram still has an exponential amount of area. It still has all of these 2 cells here. So we have an exponential amount of area. We have an exponential amount of area because of these 2 cells. But now we no longer have an exponential length to the boundary, because we got rid of that by gluing these 2 copies of the diagram together. So the area of this diagram, which I'm going to call the n, is an exponential function of the length of the word W bar n. In fact, so what we still need to do is to show that these diagrams are optimal, are minimal, because it could be that these words bound other diagrams that have a lesser amount of area. But so what we need to do is to show that the area of these diagrams is equal to the area of the words that correspond. And the way we do that is using Gersten's lemma. So Gersten's lemma says that if the presentation complex is spherical, then embedded diagrams have minimal area. So these diagrams, one can see very easily that they are embedded in the K complex. And so what's the idea of this? Why is this true? Well, if you have an embedded diagram in your KL complex, and you have another diagram that has the same boundary, you can group these two diagrams together along their boundary to obtain a sphere. But if the complex is spherical, in the universal cover, all the spheres are going to be trivial. And that means that we're going to be able to sort of make a correspondence between the cells of one of the diagrams to the cells of the other diagram. And that's going to prove that the area of the non-embedded diagram or of the other diagram is going to be at least as much as the area of the original diagram that was embedded. So using Gersten's lemma, we see that these diagrams are optimal. So this gives us a lower bound for the area for the isoperimetric function of the bond-select solitary group. So how do we obtain an exponential upper bound? We use something called corridors. So B corridors are chains of two cells that are attached together along their B letters and that do not cross. So I drew two corridors here. Here's one. Here's the other one. And we can use this to estimate an upper bound. And the way we do it is by looking at a diagram. So this is a diagram for some word W in the K complex. And if the word contains any instances of B or B inverse, then there's a corridor that connects this B to a corresponding B inverse. Okay? And because the corridors do not cross, we can look at one that is innermost of such pairs of B's or B inverses. And these are also connected by a corridor. And what we can do is that we can push out the whole corridor and the sub-diagram that it bounds to obtain a shorter word. So it's either shorter or it's longer, but it either so this part of the boundary right here either reduces by a factor of 2 to the k, or it increases by a factor of 2 to the k. But the area is being reduced on each instance of applications of these corridors, each time you remove a corridor. So the point is that after an exponential number of applications of these reductions, you arrive to a trivial diagram. And that gives you the exponential bound, the upper exponential bound for the den function of the group. So after an exponential number of applications of this reduction, we arrive at a trivial diagram. So that's the idea of how we see that the Bohm-Exciter group BS12 has an exponential Dehn function. And the interesting thing is that this phenomenon can be sort of utilized to produce even bigger Dehn functions. So we saw that the Bohm-Exciter group has an exponential Dehn function. And we can define a group by taking the original Bohm-Exciter group, adding one generator and adding one reagent, which is going to mimic the original reagent, but it's going to use a new letter. So it's going to be conjugating B to B squared. And this group is going to have a double exponential Dehn function. And we can keep doing this. So we can add a new reagent in this group. We can add a new generator and another reagent. And this group is going to have a triple exponential Dehn function. And more or less the idea is that if we look at diagrams, say in this group, in the K complex for this group, they're going to look a little bit like this. Oh, not sure what happened. Okay. They're going to look a little bit like this. So this is similar to what we had before, only that now because this group has two types of reagents, it's like we have two pieces that we're going together to obtain the diagram. And the sort of orangey yellow pieces come from the first reagent, so maybe I should. And the green pieces come from the new relation that we added here. And we can utilize sort of these two directions to obtain the double exponential. And that's the idea for all iterative, for all the iterates of this construction. And this construction has sort of limit, which is Gersten's group, this group right here. I don't know if this notation is clear, but A to the B means that we're conjugating A by B. So I've seen this in the literature called either Gersten's group or sometimes also Bohm's group. And it turns out that this group has a Dehn function that grows faster than any tower of exponentials. So that's a huge Dehn function. One remark is that this is still a one reactor group. So G is a one reactor group. It is known for one reactor groups that they have a solvable world problem. So the group has in particular a recursive isoperimetric function. And it's conjectured that the Dehn function of G is an upper bound for the Dehn functions of one reactor groups. So it's conjectured that there exists no one reactor group that has a Dehn function that grows faster than the Dehn function of Gersten's group. Okay. So now I would like to change gears and go back to talking about then functions that are bounded above by exponentials. And I want to try to understand the structure of this set. So the set of these, such that n to the d is the growth type of a then function for some group. So the first remark to make is that this set is countable. Just because we have countably many isomorphism classes of finally represented groups. And then functions are only defined for finally represented groups. So this set is countable. And other than that, what do we know? We know that it contains 1, because we know that there are groups that have linear then functions. We know that it contains 2, because we have groups that have quadratic then functions. And in general, we know that it contains all the integers. But from what we've discussed so far, we don't know much more than that. We know that there's a few other numbers around here that are then functions, because we discussed that there are no bottom groups whose then functions are not exact polynomials. But we don't know much about the structure of this set. We don't know, for example, if this set is dense in R. We do not know if it contains rational numbers other than the integers. We do not know if it contains irrationals. So we would like to explore this and find out a little bit more about its structure. So the first step is the following. So we want to know what happens in this interval right here, in the interval between 1 and 2. And we have a theorem that says that if a group satisfies a subquadratic isoperimetric function, then in fact it satisfies a linear isoperimetric function, which implies that it's hyperbolic. So there are no groups that have then functions that are subquadratic but not linear. There are no groups whose optimal isoperimetric function is in this interval. So what I'm going to do is I'm going to erase this interval from this line here. Now I just want to comment that this theorem is not just sort of an amusing fact. It has applications. It's useful to know the structure of the isoperimetric spectrum. I think I forgot to say that, but this is called the isoperimetric spectrum. And one such application is Besvina-Feyn's combination theorem. So I mentioned yesterday when I was giving examples of hyperbolic groups that sometimes when you amalgamate hyperbolic groups or take H&N extensions of hyperbolic groups, you still get hyperbolic groups. Besvina-Feyn's combination theorem gives sufficient conditions for that to happen. And I mean, the proof is very complicated. It uses many things, but in particular, it uses this characterization of hyperbolicity. Okay, so the next natural question is whether there are other gaps in the spectrum, in the isoperimetric spectrum. And it turns out that this is not the case. So in fact, the isoperimetric spectrum is dense in the interval 2, infinity. So outside of the interval 1, 2, everything else is achieved. The isoperimetric spectrum is dense in this set. And a more precise statement is the following. Oh, I'm sorry. So there are finally represented groups, which are called GRP, which are, we know them as Snowflake Groups. whose then function is of this form, where the numbers are described by a matrix, by an irreducible matrix, whose eigenvalue is the base of the logarithm here, and by a real number, a rational number that is greatest than the largest row sum of the matrix. So that's the R right here. And this statement might look a little obscure, but in particular, it implies that the intersection of Q with the interval 2, infinity is contained in the isoperimetric spectrum. Okay, so this is a theorem of, so the first version of this theorem is due to Brady and Bridson. And then Brady, Bridson, Forster, and Shankar refined this construction. And I'm going to try to spend the next few slides sort of explaining what are the elements, the ingredients that go into this theorem. I won't prove the theorem as such, but I'll try to give you an idea of what are all the ingredients that go into proving the theorem. Okay, so these groups right here, the snowflake groups, they're called snowflakes because when you look at diagrams, at certain diagrams inside of these groups, you see a sort of fractal structure. And how do we build these groups? So they are graphs of groups. So they are described by graphs, where these graphs have groups associated to each of the vertices and groups associated to each of the edges. And so on. And these are basically iterated H&N extensions and free amalgamated products. I won't get carefully into the details about the definition of a graph of groups. If you want to know about it, you can see the videos for Rayleigh's manicures from last year. But the point is that this is a way of describing groups. And the groups that we're interested in are described in this way as graphs of groups. And the vertex groups, so the groups that are in the vertex of this graph, are also going to be described as graphs of groups. And these are going to be graphs where the vertices are set square groups and the edges are infinite cyclic. So these are going to be described as racks. I think Eduardo mentioned racks yesterday. And on a line. So this is the rack on a line. Okay. And another way of viewing the definition of a vertex group is through something called the Torus construction. So I'm going to explain what the Torus construction is through an example. So we're going to start with a simplex, a finite two-dimensional simple shell complex. And in the example we're going to do, we're just going to look at a simplex, a two-simplex. And what we do, so this is K, what we do is that we take the quotient by the vertices. So we identify all the vertices to one point. And what we get is something like this. So this is K divided by K0, quotient by K0. And this is sort of hard to draw as a quotient, but it's the space you get by identifying all the vertices. And we can view it as a bouquet of circles to which we have glued a triangle. So a triangle whose boundary path, whose attaching map is given by the attaching map of the original simplicial complex. And so this is a presentation complex. It's a presentation complex that corresponds to this presentation right here. And so far, we haven't really done anything yet. So what we're going to do now is that we're going to take another triangle. And we're going to glue it to the bouquet of circles. But the attaching map in this case is going to be the one that you get by inverting the direction of all of the arrows. So this is still a presentation complex. And the group it presents has the same set of generators. It has the same original relation. And it has a new relation where all of the signs of the generators have been inverted. So what is this group? Maybe it's not very clear, but one way to see what this group is just by seeing that instead of gluing two triangles to the graph, we can think of gluing the two triangles together and then gluing them to the graph. So this is the same as taking the two triangles and gluing them together along an edge. And the group we get by doing this, the space we get by doing this is just a torus. So this is actually just Z squared. And that's the reason why this is called the Torus construction, because what we're doing is basically we are replacing each simplex in the simplicial complex by a torus. One remark is that the complex we obtain, so this is called TK, the complex we obtain by doing the Torus construction is a spherical. Okay, so what's the relation between vertex groups and the Torus construction? So the vertex group Vn is obtained by applying the Torus construction to the cone over a line. So we have a line, we cone it off. This corresponds to a vertex group in our snowflake. So the number of edges here is going to be n minus 1 for Vn. So this is a little bit of a comment on the side, but we mentioned yesterday Stallings group, which has a quadratic den function. And it can be viewed as the group obtained from a Torus construction. And in this case is by applying the Torus construction to the two skeleton of a octahedron. So this is not the way Stallings group is introduced. So its presentation, its original presentation, or sort of the standard one, is this presentation here. And it's maybe not obvious how this presentation relates to this complex right here, but you can think about it if you want. Okay, so let's keep talking a little more about the vertex groups. Another way of describing the vertex groups is by taking m-1 copies of Z per Z with generators A1, Bi for each of the factors. And we're going to amalgamate these groups together along cyclic subgroups. And the way we're going to do it is the following way. So we're going to make B1 equal to A2, B2. Then B2 equal to A3, B3, and so on. So Bm minus 2 is equal to Am minus 1, Bm minus 1. And from this description, it's more or less clear that this group is the fundamental group of a graph of groups, where the vertices are Z squared. And the edges are cyclic, infinite cyclic. And the space, the topological space associated to this graph, so the graph of spaces, is obtained by gluing together a bunch of tori. through cylinders. Okay, so that's the idea of the construction of the vertex groups in the construction of snowflakes. Okay, so let's discuss a specific example of a snowflake group, or really, I guess, rather a family. So one for each R, where R is a natural number. So the groups we're going to be looking at are defined by this presentation. So let's sort of try to figure out what this presentation is describing. So the first relation here indicates that A1 commutes with A2. So the vertex group is going to be, as we know, a set square. And these relations right here tells that it's a double H&N extension. So this is the graph of groups. The graph of spaces associated is a torus to which we are gluing two cylinders. And the attaching map of these two cylinders to the torus depends on these two relations. It's described by these two relations. Okay, so let's look at the diagram inside of these snowflake groups. Okay, so the diagrams that we're going to look at have a portion of them that comes from the tori. So they have a portion that is sort of living inside of a plane. Then they have a portion that comes from the cylinders in the graph of spaces description. And then again, they have portions that lie in the lifts of the torus to the universal cover, so in planes, and so on. So the triangles correspond to sub-diagrams that are inside of, to sub-diagrams that are inside of planes, and the strips correspond to sub-diagrams that are inside of cylinders. Okay. And what words are these diagrams describing? So this line right here, which we're going to call the diameter of the diagram. So this is the diameter. It's made of R to the K C edges. So these are all C's. And the relation we have here, so this relation, or the one on the top, whichever you want. No, actually this relation here. This is the one that I want to take now. So this relation tells us that the other two sides of the triangles are A1 to the R to the K and A2 to the R to the K. And now these two relations tell us what are the boundaries of these strips right here. So this strip conjugates B2 to C to the R to the K minus 1. And the same in this side, only with B1. And what we can see here is that we have gone from having C to the R to the K to having C to the R to the K minus 1 in the next triangle. So if we iterate this construction, on the next level, the base of the triangle has length R to the K minus 2, and this is for each of the triangles, and so on. So the point is that if we keep this process until we until we cannot sort of continue it anymore, we get to triangles whose base has length 1. So all of its sides, of their sides have length 1. And we have as many triangles as many edges the dual tree has in that sort of level. And that's going to be about, so the triangles, a number of triangles in the last stage is about, so let me put it this way. The number of triangles in the nth stage is about 2 to the n. So that's the way we do it. And the point of this is that this diameter right here is long. So it has, this path has length r to the k. And the path that we obtain by instead going around this side has length about r to the k minus 1. No, about it's about 2 to the r to the k minus 1. So for k large enough, r to the k is larger than 2 to the 2r to the k minus 1. And when we continue this process, we're shortening the path at each stage. And the way this is useful is because we can glue 2 copies of this diagram together to get rid of the long edge, to get rid of the diameter here. So this is the sort of diagram we obtain. And the idea is similar to what we did with the Baumstark solitary group. So we had a diagram in which we could control the length of the boundary through most of the boundary, but we had a part of the boundary of the diagram which was very long. And we didn't want that, so what we did is that we take 2 copies of the diagram and we glued it together along the long path so as to obtain a diagram whose area is related in a certain way to the length of the boundary. So that's what we do here. And now we want to estimate the area of this diagram. So first of all, the length of the diameter. So the diameter, we have it here. I'm going to call it d. So the length of d, it grows as r to the k, as we discussed. And the area of this diagram, it's at least as much as the diameter, as the square of the diameter. So, and this is because inside of the planes in the universal cover, so these 2 triangles that you see here, these 2 triangles are inside of a plane. So the area inside of that plane relates quadratically to the length of the boundary. So that's why we get this estimate here. And the boundary, the length of the boundary of the diagram, because we have gotten rid of this long diameter, the length of the boundary is related to the growth of the dual tree. So that's not a very good drawing, but the length of the boundary is related to the growth of the dual tree. So the boundary this is about 2 to the k. And all of this together give us an estimate of the area of a sequence of diagrams. So let me just recap. We know that the diameter goes as 2 to the k. The area is the square of the diameter. And the length of the boundary grows as the dual tree. So it's 2 to the k. And that gives us a lower estimate for the area of each of the diagrams in this sequence. And this tells us that the den function of the group is bounded below by the following function. So it's n squared times the logarithm base 2 of r. So let me sort of recap what are all the elements in this function, where they are coming from. So the n squared comes from the flat planes. So it comes from the fact that the vertex groups in our graph of groups are tori. And this is going to be the same not only in these examples, but in general in the Snowflake groups. Okay. The base of the logarithm has to do with the growth rate of the dual tree. And the r right here, this r comes from the attaching maps from the cylinders to the tori. So you can also think of the r. So the r is, if you remember, it's the power that we're taking of the A1 and the A2 here in this presentation of the group. So this describes more or less how we obtain this estimate on the den function of this class, class of examples of Snowflake groups. So I remarked at some point that the vertex groups are spherical, and in fact, the whole space, so the space dealt from the tori and the cylinders is also spherical. So again, we can use Gersten's lemma to conclude that these diagrams that we have been discussing are optimal. And for the upper bound of the den function, one can again use corridors. So to study the structure of these diagrams. So this is more or less the idea. And I want to discuss another ingredient. So this is just for the particular example that we had right here. But if we go back to the statement of the theorem, the general construction involves a matrix, an irreducible matrix, and it speaks about the Perron-Frobenius eigenvalue. So this might be a little bit mysterious, and I want to sort of mention how it's related to the construction. Okay, so let me remind you, a matrix, a non-negative matrix, is irreducible if for every entry in the matrix, there is a natural number, a real number, such that, well, a natural number such that the matrix to that power is positive. And there's a theorem of Perron and Frobenius which says several things. And two of the things it says is that when we have a matrix of this kind, it has a real positive eigenvalue whose value is larger than the absolute value of all the other eigenvalues of the matrix. This is called the Perron-Frobenius eigenvalue of the matrix. Okay. Now, a transition matrix is a matrix that you obtain from a graph by putting in the entry I, j, the number of edges that go from I to j. So it's a square matrix. Here's an example. We have a graph here, and the associated matrix, transition matrix, is this one. And in the other direction, we have a matrix here. It's associated graph. This is the transition graph of this, the transition matrix of this graph. And the matrices in Brady-Bridson, Forster, and Shankar's theorem are transition matrices. Associated to the graph of groups. So I hope this gives a sort of idea of where all the ingredients of the theorem are coming from. Okay, so I just want to revisit quickly the isoperimetric spectrum with the new information that we have acquired. So we know that there's a gap in the interval from 1 to 2. Other than that, we know we knew from the beginning that all the integers were in the set. And we know that IP is dense in R. So we can color in basically the whole line. For values larger than 4, we actually have more information. So there are theorems of Birget, Sapir, and Olshanki that describe in more detail what sort of numbers can arise in this interval. So in the interval 4, infinity. I'm not going to get into that, but I just wanted to mention that nowadays we have sort of much more precise information on what kind of functions can be isoperimetric functions in these, can be dense functions in this interval. Okay, and to finish, I would like to just sort of talk a little bit about a different topic, which is that of dense functions of subgroups. So it's very natural, once we understand an invariant of a group, to ask ourselves how that invariant behaves under subgroups. And we're going to focus on hyperbolic groups because they are very nice and we understand them very well. And if all the subgroups of hyperbolic groups were hyperbolic, then the subgroups will all have linear dense functions. Now, we know that this is not true because a hyperbolic group contains infinitely generated groups, but that sort of doesn't count. We want subgroups that are finitely represented. We want subgroups for which the dense function is defined. And it's a theorem of Brady that there are subgroups there is a hyperbolic group that has a finitely represented subgroup that is not hyperbolic. And so this does not give us very direct information on the dense function of this subgroup, but it does tell us that this subgroup, that the dense function of this subgroup has to be at least quadratic. So we know that. And we also have a sort of bound on how complicated that dense function can be. So the group in this theorem arises as a group in a split exact sequence of this kind. And that implies that the then function of this group is at most polynomial. So this is a theorem of, I think also of Brady, I think, or maybe of Short. So we have subgroups of hyperbolic groups whose then functions are defined and are not linear. And we also have an understanding of how bad they can be in these examples. It's not known if other things can happen. So we can have obviously hyperbolic groups that do not arise in this way from these kind of split exact sequences. But it's not very clear what else can happen because we don't have many examples of finely represented subgroups of hyperbolic groups that are not themselves hyperbolic. So this is sort of the only example that we can really discuss. And I think I'm going to finish with that. Thank you very much.
Thank you. Do we have any questions for Macarena?
Do you want